lecture. So this will be the third lectures of Marcos Mariño on Resurgent methods in string theory.
Okay, so let me first make a small comment that I forgot yesterday. So yesterday we were analyzing this solution of Paul-Levé 1, right? So we found that the kind of more complete solution has a perturbative piece, which is what people studied in the old days. And then there was a series of corrections that could also be found from Paul-Levé 1. And in particular, we saw that that U1 was actually of the form kappa to the 5/4. And at the same time, we also saw that by looking at this perturbative series, by using the standard methods that we developed in the first lecture, we found a singularity here precisely at this value of A, which is supposed to agree with this. So you see, there is, what we did yesterday also, I hope it was clear, we actually did we derived the non-perturbative effects in actually two ways. One by looking at the resurgent structure of the perturbative series, and the other by using a trans-series solution of the Paul-Levé equation. So these methods are logically independent, and they give the same answer, okay? So what I was telling you is, okay, in order to solve the problem of understanding this trans-series, let's actually use a trans-series answer for the Paul-Levé 1, because this looks like a nice principle. But at the end of the day, this is a non-trivial mathematical statement. Why the analysis of the perturbative, of the large order behavior of the solutions of the perturbative piece agree, the trans-series that you associate to this singularity is the same one that you find when you do this trans-series answer. This is non-trivial mathematical statement. And actually, the fact that this is non-trivial is also emphasized by the fact that Ekal, who is one of the mathematical fathers of the theory of resurgence, actually derived this statement, proved that this is true by using what is called a bridge equation, okay? So the bridge, according to Ekal, is a bridge between asymptotic analysis and a study of the trans-series solutions to the OD, okay? So Ekal has a kind of a talent for inventing nice names. So there is the bridge equation, there is the trans-series, alien derivatives. He has invented a lot of, it's a very French art of inventing fancy names for things, okay? So he actually introduced many of these names. And the bridge equation is one of these, and it's actually the bridge between asymptotic analysis and OD analysis. So essentially, what he shows is that you can analyze there is a relationship between analyzing singularities by asymptotic analysis and the sort of corrections to the differential equation. So this is a bridge between differential analysis and asymptotic analysis. Okay, so this is the mathematical statement that was underlying actually the method I proposed yesterday. Okay, so are there any questions on what I have been doing so far? Because today I'm going to change a little bit the topic. So now, once we understand, how resurgent works in very simple models of 2D gravity, the question is what would you do next? And what I propose to do next is actually something which is going to make connection with the lectures by Rajesh. So we are going to look at matrix models, okay? And in particular, we are going to look to the one matrix model that Rajesh introduced. So I'm going to, unfortunately, we're not going to use the same notation, so it's the same thing. But so the matrix model I'm going to use is exactly the same that Rajesh was using, just with a slightly different notation. So this is an integral over Hermitian matrices, and then I'm not going to introduce an n here. I'm going to introduce 1 over GS, okay? And then I will have a potential of this form, okay? So here GS is going to be my parameter expansion. This is a normalization, which is the volume of UN. And then, we can study, as Rajesh did, the one-cut sector, okay, or the one-cut matrix model, in which we take n to infinity, we take GS to 0, and we fix this parameter T which is the product of GS times N, which is called the top parameter here, okay? So, so this is, again, slightly different from what Rajesh did, but this is just in notation, because you see, I'm going to take GS going to 0 with T fixed, and he was putting an N here and was taking N to infinity, so it's the same type of limit, okay? Just there are going to be maybe some difference in the notation, and the statement is that in this limit, the free energy, which is the logarithm of this partition function, is going to have an asymptotic expansion of this form, fg of t, times gs to the 2g minus 2. So again, you know, Rajesh, I think, was using the expansion in 1 over n and doing the expansion in, so around n equal to infinity and doing the expansion in gs around gs equal to 0. But, you know, since I'm keeping this thing fixed, it's the same thing, okay? Now, this is the kind of quantities that, Edward and Rajesh were showing us they can compute with this amazing method. So these are going to be functions of t, you know, with a finite radius of convergence, as I was explaining yesterday. But as I was also emphasizing yesterday, with t fixed inside this radius of convergence, as you vary the genus, this is going to go as 2g factorial, okay? So now one kind of question that you could ask, this is maybe not directly as a string theory, it's a matrix model, but we know by now that matrix models are dual to string theories in many cases. So maybe in order to kind of try to go beyond 2D gravity, one thing that we can do is, okay, what is the resurgent structure of the 1 over n expansion in matrix models? That's a kind of natural question that one would ask as next in complexity to what we have done so far, okay? And since matrix models are dual to string theories, in many cases, this is going to give us some understanding of non-perturbative effects in string theory by using resurgent methods in large matrix models, okay? Now, let me actually mention that I will actually use very often the eigenvalue representation that was sort of implicit in Rajesh's position. So I'm going to write this. This is essentially going to the, so I'm going to diagonalize my matrix M. I'm going to write it as a diagonal matrix, lambda 1, lambda n. So when you do this, this is like fixing the gauge. In gauge theory, you think about this as a zero-dimensional gauge theory. So what you get here is a product of these eigenvalues divided by 2 pi, 1 n. Then you have here the van der Monde determinant. So delta of lambda is the product of ij lambda I minus lambda j. And then here you will have this thing here. And this is actually a good thing to do sometimes because here we have an integral over n square variables, and here we have just an integral over n variables, okay? So I'm going to use this, this representation from time to time. But what we can try to do in order to understand this problem, you know, if you want to understand how these things grow with the genus, maybe the first thing to do is to look at the simplest matrix model you can think. And the simplest matrix model is, of course, the Gaussian matrix model, okay? The Gaussian matrix model is the model in which V lambda is lambda squared over 2. And, you know, you can normalize things always so that this model has a partition function equal to 1, but this is not what I'm going to do. I'm normalizing my things in this way, and actually you normalize things in this way, the partition function of the Gaussian matrix model is a non-trivial function. So it's actually a very beautiful function. Let me write it here. So Cg, actually this depends on Gs and N, so let me write it here as C of NGS. So this can be evaluated exactly. There are many ways in which you can do that. You know, one way is just to do this integral by using, say, orthogonal polynomials. Another way to understand is that, you know, this integral is actually trivial, and all the meat is actually in this normalization factor. So, you know, I'm using an appropriate normalization. But in any case, you get this very beautiful formula. So you get an overall power of Gs. You get this, and then you get here G2 of n plus 1, and this guy is the Burns function, okay? So the Burns function is like a generalization of the gamma function. If you have never seen it before, it's a nice function. And you can essentially define it by the property that, so you see it's an upgrading of the gamma function. The gamma function has such a property that you don't have gamma n, you have n. So this is like, it's like the gamma function is a product of I from 1 to the n, and the Bernoulli function is the product of I factorial from 1 to the n. Okay. Now one of the good things about this thing is that since you have a exact formula, you can now try to calculate the SFGTs, right? You can just try to expand this at large n. So this essentially amounts to the problem of calculating the asymptotic expansion of this function at large n. And then if you do this, it's a very easy exercise, you will find that fg of t actually has a very beautiful formula. It's given in terms of Bernoulli numbers of 2g times 2g minus 2 to the 2 minus 2g. So this is the formula when g is bigger or equal than 2. For 0 and 1, genus 0 and 1 are a little bit special. F0 of t, for example, it's also a nice formula, t squared over 2 log t minus 3 halves. Okay. So, so these are really, this just comes from the asymptotics of the Bernoulli function. So these are the kind of things that, you can do easily by just checking your favorite book on special functions or asking an AI chat, right? Okay, so now we have a very simple formula here, and the first thing you have to check is this 2g factorial growth. This is what we expect. We expect to have a 2g factorial growth, and indeed we have a 2g factorial growth because the Bernoulli numbers turn out to grow factorially with 2g. Okay, so we already have this, but we want to do better than this. We want to really understand the location of the Borel singularities for this asymptotic series, right? This is an asymptotic series, right? What we have here as a series in GS, and we want to understand, where are the singularities. And this is an example which is interesting. This looks like very trivial, but it's interesting for two reasons. First of all, because it's an example where you can do everything very explicitly. And the second reason is that this type of behavior is also the behavior of topological strings near the conical point. Okay? So this will give us some mileage for the discussion that we will have tomorrow on topological strings. Okay? This is, in a sense, something that it's a preliminary thing that we have to do in order to understand topological string theory. Now, let me call this number B to G. And now, you see, we could try to do the Borel resummation, but what I'm going to do is the Borel transform, but I'm going to use, exceptionally, a slightly different version of the Borel transform that I used the last time. And the reason is very simple. Let me just explain you what we are going to do. So you can actually introduce, let me actually write it in full. If you have a formal power series like this, we introduce this Borel transform, which was phi hat of psi. We were just taking this an, the other n factorial zeta n. Okay? So this is actually what physicists mostly use for Borel transform, but you can actually use a slightly different version. You will see it's a trivial thing, in which you actually take the coefficients starting with n equal 1, you take an, you divide by n minus 1 factorial, and you take this, okay? And this is so trivial because, this is actually just the derivative of the other Borel transform, okay? So this sometimes is more useful to use, and you see it's very trivial because you pass from one to the other very easily. But you see, the reason why I'm introducing this is because sometimes this is actually easier to calculate in closed form than this, because this is actually, phi hat is a primitive of this function. And calculating primitives is not so easy. So sometimes you might know a function, but you might not its primitive. And this is exactly what happens here, okay? So you calculate this, it's a very easy thing that you can do. Now you plug these, for example, numbers in Mathematica, you will see immediately, it will give you immediately the answer. So here, I'm going just to pick, and just to, since I'm interested in the large order behavior, I can't forget about F0 and F1. So I'm going to start with I can put A0 and A1 to 0, and I'm going to start with the coefficients starting with G2. And you have to also to be a little bit careful because this is multiplying GS to 2g minus 2. So this is actually the exponent that we have here. So there is a slight shift here. So actually, since this is 2g minus 2, n minus 1 is 2g minus 3 factorial, okay? And here you have zeta to the 2g minus 3 factorial, sorry, 2g minus 3. And then, this can actually be computed in closed form. It's a beautiful formula. So this is one of the few cases in which this can be computed very explicitly. And then, here, actually, sorry, the B2 includes everything here. It's the whole thing. It includes also the t, the factor of t, which is going to appear here. Let me see. I have the feeling that I have a misprint in my notes, in my handwritten notes. So let me see. Yeah, there was a misprint in my handwritten notes, but this is not a problem. T squared over psi squared. And then I have minus 1/4 of sinh squared psi over 2t, okay? So that's a very beautiful formula. It's very explicit. And you can see the singularities immediately because you have a sinh square, so you will have double poles, okay? Now the fact, since there are double poles in phi twiddle, this means that there are going to be simple poles in phi hat. You could now, and you see the primitive of this function is very complicated to integrate, right? So you cannot write it in closed form. But in order to analyze the singularities, you have the same information. So you see that the singularities are double poles, which is a simple situation, right? So this means that the trans-series are going to be very simple because complicated trans-series, complicated information in singularities only appear when you have log of branch cuts. So you have simple poles. The only information is the residue, okay? So you have singularities are double poles at psi divided by 2t is equal to pi I L. This is absolutely regular at psi equals 0. You can see that this term here eliminates the singularities here. And then, so this L is in Z minus 0. So this is the location of the singularities. So you look at the structure of singularities here, you will see that they are, this is a very beautiful pattern. So you will have here a tower of singularities here and a tower of singularities here. So the structure in the structure of singularities in the Borel plane is very nice. So you have this 4 pi I t dot dot dot. Okay. And now where are so the obstructions to Borel resummation are going to be in the imaginary axis. So one thing that you can compute is just simply we could compute things. You remember the information of the singularity, we can encode it in different ways, but the most powerful way is to actually calculate the Stokes discontinuity. So let me actually compute the Stokes discontinuity here in between these two paths, C plus and C minus. Now, if you are using this Borel transform, the formula for Borel resummation is slightly different. You see, I want to have the same, yes? Sorry?
The first factor there is what?
Yes.
In phi tilde. No, after the equal.
Yes.
Is 1 over z?
1 over zeta, yes.
But so what happens at z equal to 0?
I told you, this is regular. When you expand this,
That
you
is
will
regular?
see.
Okay,
Yeah.
but it vanishes.
What is vanishes?
The parentheses. I mean, there is a pole, a simple
zeta
pole.
is equal to 0. No, this removes the pole here. Here there is a pole of order 2 and an additional 2.
Yeah, but in front there is a pole, a simple pole, no?
No, but this is going to be of order psi, zeta. You just have to.
This is?
This is of order zeta. No, there is no pole at zeta.
This is order zeta. Okay.
No, I told you, the pole at zeta equals 0 is removed by this.
Okay.
You just have to expand
Thank
it.
you.
It's not obvious. And I hope I didn't make any mistake, but I think this formula is correct. And if you expand this, you will see that the whole thing is of order zeta, and then, this is cancer. There is no singularity. This starts as zeta 1, right? Actually, you should get you should reproduce this series, so, okay? And the poles are actually away from 0, okay? So when you do this phi twiddle, you have to be a little bit careful because you have to do a slightly different form for the resummation. So you have to actually do it. It's actually again a very simple thing. You just don't have the 1 over zeta here. Okay. So now it's a very beautiful simple calculation to do this because you see when you do the difference s plus minus s minus along these contours here, you see. You can see that you can see what are the, you can actually pick the residues of the poles, and this is a very beautiful answer. So you actually get 2 pi I, the sum over L bigger or equal than 1 of the residue at zeta equal to 2 pi I LT of phi twiddle z e to the minus z. So you have this, and then you can, you know, this is a very simple calculation, and what you get, it's actually I over 2 pi, the sum of L bigger or equal than 1, and this residue is very easy to calculate, so I get this formula here, which has to play a very important role. Okay, and here A is the position of the first singularity. Okay, so actually this is a very nice formula. It's telling you that at each singularity here, okay, there is a transeries which is an exponentially small thing, right? And so L here is 1, 2, and so on. You have a transeries which is actually very small. It gets truncated. At first, there are only 2 terms. And this is a result that was first obtained by Sara Pasquetti and Riccardo Schiappa. And I call these Pasquetti-Schiappa instantons because these are really look like instantons, right? You know, you have 1 over GS3 here, and you have here this factor, okay? So this is a very beautiful formula because we will use it later to understand topological string theory near a conical point. Yes?
I just want to understand about the imaginary, them lying on the imaginary axis. So these seem to be very universal because it's just expanding this log volume
yes.
n, basically
yes.
large n, right? But they're at imaginary values of n, essentially? These...
No, this is on the Borel plane. Huh? This is the Borel plane, it's not the physical plane.
Yes.
But of course, the Berns function is an analytic function, it's a complex function of its argument, So yeah, you could actually do it.
The action of these instantons is for real G-string?
The action of these instantons is proportional to the tough coupling, which you are keeping fixed in this thing, okay? And they are imaginary. I mean, the singularities can be anywhere, right? That's something that, But of course, what is distracting? What is disturbing you?
I guess it's the e to the action is imaginary.
Oh yeah, but this is not a problem because there are complex instantons in life. And also notice that I'm not telling you what is GS, right? If GS is imaginary also, this is actually a real thing. So it's fun, yeah, but complex instantons exist, right? There are instantons with complex action, and they are important. This is another case in which they are important. Borel singularities can be anywhere, right? So an instantons, this is not the kind of instanton that you would calculate by doing a kind of trivial WKB calculation or something like that. But we already saw, for example, in the discussion of quantum mechanics, that you get a sort of real tunneling only if the coupling constant was negative. If the coupling constant was positive, you also have some sort of,
positive action.
like the tunneling was hidden in a sense. So sometimes you have to tweak the value of your coupling constant until your instantons become real. And here, for example, I know if GS becomes imaginary, this exponential factor will be kind of exponentially suppressed quantity. So sometimes instantons can have different signs or reality properties that only appear as exponentially suppressed quantities for special values of the couplings. Okay.
So the fact that the Borel transform only had poles and no branch cuts,
yes.
I guess that's what allowed you to kind of treat all of these together. Otherwise, you would have probably had to do one singularity at a time and kind of?
Not necessarily, not necessarily. You can actually have a trans series in which you can actually resum the full series. And for example, in this the Lavaer-Dillinger-Fan formula, which is a formula that appears in WKB, you have non-trivial trans series at each point, but you can actually sum over the full tower.
But then you have to choose some sheets, right? I mean, then you will.
No, not necessarily. No.
You take a contour in the original one, and then you kind of.
Remember that I mean, here of course you have to take the branch cuts in the right direction, but remember that all this information is important. Is really local. It's really a local information. So as long as you encode it.
Here in the pole, it's of course very clear.
Yes.
But I was wondering, is that there's a simplification because the only singularities are poles?
Yes, but of course, but for example, just to give you an example in WKB. In WKB, it turns out that the series is something like this, right? Something like, and then you have e to the minus L, and here you have this Borel symbol, right? And this is a non-trivial function of h bar, right? But still, you can sum this, right? This is a log, right? So the fact that this has a non-trivial, properties. I mean, can be a very complicated thing. Still, there are in a sense two different things here. One thing is what appears in this term, and the other thing is how these things organize for different. There are two different things. One is the complication of the instanton, of the one instanton thing. So L equal 1 equal 2. And the thing is how the multi-instantons get together. You see, here the multi-instantons get together in a nice way, and here they also get together in a nice way. So this is a log. This is a log of 1 plus e to the minus nu h bar over h bar, which is this famous de Lavaer-Dillinger-Fan thing. And here actually, you didn't see it, but this is a very beautiful formula. If you sum it, is the log of the Fadeyev's quantum dilogarithm of e to the minus a over gs. Okay, so that's also it's a very This is for those who don't know you. This is one of my favorite functions. Is the Fadeyev's quantum dilogarithm. Okay, just for the value of the Fadeyev parameter equal to 1. Okay. Okay. So this is really a very nice result, and essentially solves the problem of understanding the Resurgent structure of the Gaussian matrix model. But this is not a big thing, right? So most of the matrix models are not Gaussian. So what do you do if your matrix model is not Gaussian? Well, then you have to work a little bit more. So let me actually tell you how you would try to address this problem in the more general models. And this will actually hopefully make contact with many of the things that Rajesh explained to us today, okay? And in all these lectures, okay? Okay, now, so what we are going to try to do is to generalize the saddle point method to matrix integrals. And actually, one very beautiful way to look at one-cut matrix models is as generalizations of one-cut matrix integrals parameterized by the Toff coupling. So the way to do this is to actually reorganize these integrants by writing in this way. So I'm going to write it as minus 1 gs, the sum over v lambda I, and then I'm going to put the van der Monde determinant in the here. Okay, let me actually make it again sure that I'm not. Yes, that's okay. No, actually, this is gs. No, this is actually okay. T over n. Then you have I different from j, and then you have the log of lambda I minus lambda j squared. So I'm just putting the van der Monde in the exponent. So I can now think about, that's already very interesting because you see that if t goes to 0, okay, if t goes to 0, then the matrix integral becomes just a product of, an actual product of one-dimensional integrals to the power n, okay, where this integral is just 1 over 2 pi, the integral of e to the minus v lambda, 1 over gs v lambda d lambda, okay, over 2 pi. So when t goes to 0, essentially, what you have is you factorize your matrix integral into a product of n integrals that you can study individually by using the saddle point method. So I'm going to assume that these integrals can be analyzed around the saddle point, around a point lambda equal to x star, which is a critical point. It's a critical point of V, okay? So my favorite example in these lectures is going to be the cubic matrix model. And in the cubic matrix model, I'm going to take this. So an example of this is V lambda is equal to minus lambda plus lambda cubed over 3. So this is a potential like this. And I'm going to consider a theory in which these one-dimensional integrals are actually expanded around x equal to 1, okay? And here there is another critical point, which is x to the minus 1. But I'm going to consider this thing in this way. Now, if t was 0, all the eigenvalues are going to be eigenvalues in individual integrals. They are going to be all located here, right? So when t goes to 0, essentially all n eigenvalues cluster around this point, okay? Now, what is the effect of turning on t? As you start turning on t, this term here will start acting. And this is actually a repulsion between these lambdas. You can think about this as a global potential. So the eigenvalues are here. You turn t to 0, and all the eigenvalues are here. But when you turn on t, the eigenvalues start to have repulsion, and then they are going to get distributed. They cannot be all together. It's a sort of like Pauli exclusion principle. And then what you will find is that for finite t, what you find is actually a distribution of eigenvalues, okay, which is going to be around. So if you have this point in which you are doing this thing, this is the kind of saddle point or critical point when t is equal to 0. The eigenvalues are going to get distributed in a shape determined by a density function, okay? So this density function is going to be normalized, and there will going to be an interval here, c equal ab, and this is normalized to 1, okay? So this, I think, Rajesh has mentioned this in his lectures, and this is something that I'm going to use. And now you can say, okay, how do you determine this density of eigenvalues? I added to my notes a full appendix where this is derived, but let me give you a very kind of cute way of getting this. You see, you can think now about this as an effective potential acting on eigenvalues. You see, on each eigenvalue lambda I, you have the action of V, and then you have the repulsion of all the other eigenvalues. Now, at large n, this means that the eigenvalues are going to be distributed according to this thing, and it's very easy to see that you will get a potential acting on the eigenvalues, which is just the continuum version of this formula. So here, you just have V of lambda, then you have the 2t, and then you have this sum over all the eigenvalues, but the sum over eigenvalues when n is large becomes an integral with the density of eigenvalues, and then you get this formula, rho lambda prime log of lambda by lambda prime, d lambda prime on C. And then what is the condition that eigenvalues arrange themselves into this shape? Well, the effective potential on these lines, on these segments should be constant, okay? That's the, so V effective of lambda should be a constant. When I mean constant, I mean something independent of lambda on Z, right? Because, this means that they are all equilibrated, so they are in an equipotential line, and then, this means that V prime effective lambda is equal to 0, and then by looking at this expression, you find this beautiful formula, which is 2t principal value of the integral just take the derivative with respect to lambda here, And then you get this formula here, okay? So I have a principal value because I want to avoid lambda equal to lambda prime. And this is precisely the formula that BIPZ, Brezan-Istison, Parisian-Joubert, obtained in their famous 1980 paper to describe the planar limit of a one-cut matrix model, okay? So here you have a sort of quick derivation, which is very physics, right? Very physical, you know. We think about eigenvalues as, you know, submitted, you know, under the action of an effective potential, which is the potential, original potential, plus the repulsing of eigenvalues. And then this is the equation you have, okay? Now, let me give you an example. I don't explain now how to solve this equation. This is what is called an integral singular equation. But, you know, one of the things that BIPZ did was to develop various techniques to do this. This is what I'm not going to do here because, you know, that would be, you know, my lectures will become lectures on matrix models, and this was not the goal. But you can actually look at the appendix of my notes, and you will find there all the formula that you need in order to solve this equation. There are very beautiful formula, and we are going to actually to use some of them. And I'm going to also make contact with things that Rajesh said, so this is going to be very good, okay? So let me give you an example, which is the most famous one. So this is an equation that determines rho as a function. You give me the potential, I can determine rho, right? And the most famous example is the Gaussian matrix model itself. The Gaussian matrix model has a non-trivial distribution, and this is this famous semicircle distribution, 4t minus lambda square. So this is Wigner-Dyson semicircle. And let me just give you a picture of how this goes. I mean, it's maybe slightly, I mean, I really like matrix models, so I cannot, let me indulge in a bit of explanation of how this goes because it's very beautiful. So you have a Gaussian potential, right? So you have this quadratic potential, things like this. So as I told you before, if t was equal to 0, then the eigenvalues, the individual eigenvalues of this matrix would just fill this overall lambda square potential, and then, you know, in order to have minimal energy, they would all be here, right? Now, if t is different from 0, they are going to spread, and the Wigner semicircle law tells you very exactly how they are going to spread. They are going to spread in the form of semicircle, and actually you see the streams of the semicircle are actually 2 square root of t and minus 2 square root of t. So you see, when t goes to 0, this squeezes to 0 size, which is what you have to have, okay? Now, this is in general for the one-cut matrix model that we're using. Actually, this density of eigenvalues has a universal form, which is given by this m lambda, where this is a polynomial in lambda, okay? And then you have something that I'm using lambda as a variable, sorry. So you have very simple dependence on the endpoints of the cut. A and B are the general endpoints of the cut. And it turns out that for the one-cut phase of the matrix model, this is also this for a polynomial times this. And actually here, you see essentially an equation, which let me write like this. I'm just going to take this in the conventional order. So here there is an algebraic equation in disguise, and this is the famous spectral curve that Rajesh was using, okay? And so this is a spectral curve has essentially the same information as the density of eigenvalues. But there is a small bonus here, and the small bonus is that remember that this density of eigenvalues was normalized to 1, and if you express the normalization of the density of eigenvalues in terms of y of lambda, you find this very beautiful formula. Okay? Now, this is trivial, it's the condition of, but we can read this formula in another way. What is this? This is a period of a differential, period of yx dx. And this was the location of the instanton that we saw in the Gaussian matrix model. Okay? So this is the instanton. So this is one of the leitmotifs, as Wagner would put it, of my lecture. No, of my lectures is that locations of singularities are periods of some object in the theory. Okay? And here, remember, the location of the singularity in quantum mechanics was the period of the Liouville-1 form on a tunneling cycle, and here we have already this. Okay? Very good. Now, is there more stuff under the sun here? Well, there is actually much more stuff because, once we have potentials which are sufficiently complicated, this function is going to be non-trivial, okay? Now, how do we get non-trivial sectors by doing saddle point integrals? We look at other saddle points. Right now, all these results, we're assuming that my eigenvalues were near the original saddle point that I was choosing, right? But how do I get another sector in an integral, in a one-dimensional integral? I look for other saddle points. Now, you're working in a matrix model, you should look for additional critical points of V effective, because this is the effective potential that eigenvalues fill, right? Now, it's there is actually a very nice equation that you can derive with this technology, which tells me that the derivative of the effective potential lambda is actually equal to y lambda, okay? So you see that I get critical points from zeros of the polynomial that multiplies of m lambda, okay? Now, of course, you see, in the Gaussian matrix model, this polynomial is 1, so there is nothing else, okay? But as soon as you have a higher order potential, you can have zeros of these functions, and you will have additional critical points, okay? Now, for example, let me take this cubic example here. So in the cubic model, in this cubic potential, m lambda is actually lambda minus x0. x0 is a parameter. Remember that everything here is going to depend on t. So x0 is a non-trivial function of t. But what happens when t goes to 0? This goes to -1, which is the other critical point here. So what will happen in general is that if you have a potential like this, the effective potential will be a t deformation of this effective potential. So what you would have, this is what happens for V lambda. In the effective potential will have a slightly different form. Let me write it with color chalk. So the effective potential will be constant on an interval around x equal 1, because this was our original saddle point. And then it will be some sort of deformation of this, okay? And it will have another critical point at a point x0, which is a deformation of x equal to -1, okay? So how would you get another sector of the theory, a non-perturbative sector of the theory? Well, it's very easy. We just have to take one eigenvalue that we have here, and instead of integrating it around x equal to x star, we want to integrate it around the other critical point, right? That's how we would get an additional non-perturbative sector, okay? So, so what would be, non-perturbative sectors of the one-cut matrix model take one eigenvalue of the cut and put it on a 0 of mu lambda, okay? And this procedure is called eigenvalue tunneling. Okay? So that's how non-perturbative effects appear in the one-cut matrix model. Now, let's do an estimate of the exponential weight of this configuration. Okay, this configuration should be exponentially suppressed with respect to my original configuration, but I can actually get a very easy estimate of the exponential suppression, because the only thing I have to compare is, these are here I'm integrating. I have here the exponential of this effective potential, so I have to compare the effect of having an eigenvalue here versus having it here. So that's the exponential suppression I will have. I mean, here, remember, in this interval, right? This is the same as evaluating at V, because on the whole interval, this is constant, okay? So this is the exponential suppression that we will get by doing eigenvalue tunneling, okay? And now, yet another beautiful formula. Since, this is something that you can derive from the one-cut matrix model for, formalism, V effective, the derivative of V effective is y of lambda. The additional, so this is what you would call the instanton action. Now, this instanton action is going to be given by the integral from a to x0 of y lambda d lambda. Okay. So when you do eigenvalue tunneling, there is going to be a non-perturbative sector, and the exponential factor that controls this sector, the exponentially small term that you will get, is going to be is going to be an instanton action. So, this is going to be of the form that we already know. Notice that this is non-perturbative in the GS coupling, and this action is given by a period integral also on the same spectral curve. So there is actually a very beautiful geometric picture at the end of the day that you can have. Actually, you can see that this spectral curve for the one-cut matrix model in general is going to be a pinch curve, okay? And this just comes from the fact that, this has an m square. This is just the square of this. This is just because, you have like double zeros here. So in general, the spectral curve, let me actually write it in. The spectral curve for the one-cut matrix model will describe a pinch Riemann surface like this. So here you will have A and B, okay? And here you will have x0, and then you get a period for this. So you will get a period here, which is 2 pi it, and then you will get a period like this, and this is going to be A, which is the integral from A to x0 of yx. Now, this pinch curve is not the same one that Edward and Rajesh were describing today. They were talking about Riemann surface on the walls. This is a Riemann surface on the target, okay? But that's the geometry you have. And again, very importantly, instanton actions in the one-cut matrix model are periods of a natural differential form which comes from the spectral curve, okay? That's actually a kind of unifying story. So one thing that I propose you to do in the lecture notes is to do this calculation for the one-cut matrix model. So let me actually, so how much time I have? Just until 20, okay, very good. Oh, it's very good. Maybe I'm going too fast. I don't know, maybe there are questions now. Yes? Sorry? Okay, yeah.
So, two questions. So this happened for the two-cut too? You have that contribution for the instantons?
Yeah. Now, in the two-cut, what you can have is, instantons go from one cut to the other, okay?
Okay.
And, there is also a similar formula like this, okay?
This changed the phase transition, the third order phase transition or something, or?
No, I'm not talking here about phase transitions. And just, you have a background in which you have a fixed number of eigenvalues on each cut, and then you take one eigenvalue from one cut to the other, then you will have, this will be exponentially suppressed or enhanced, and the measure of suppression or enhancement is given by the difference of potentials between one cut and the other. Here, you can think about this as a cut which has degenerated to a single point, okay? But you also will have, for the two-cut matrix model, you will have a similar formula like this, okay? But there are some important differences with respect to this. I mean, for the detailed calculation of the amplitudes, the two-cut matrix model is much more subtle, okay?
So another one is that these matrix models usually come from localization, for example. Can you learn something from the field theory from these instantons?
I mean, your matrix model comes from localization. You might actually be able to, of course, to interpret this in terms of quantum field theory things, but this is quantum field theory at large n. So this would be large n instantons, okay?
Yeah, okay. Thank you.
Okay, so so let me actually maybe make some comments on what happens in the cubic matrix model. So the cubic matrix model is sufficiently simple that you can actually write down everything quite explicitly. So as I said, this function now is linear, and there is this x0 that you can express explicitly in terms of A. So you can actually calculate A. You can calculate this instanton action. Remember that in the cubic matrix model, the eigenvalue tunnelling is going from this cut to this point here. So you can calculate this AT very explicitly. And the formula you can find in my lecture notes. But the formula is not very illuminating. What is interesting is to see what is the shape of this instanton. Okay? This is actually, strictly speaking, what I would call a large n instanton. This is an instanton which is appearing in a large n theory, and its action is not a number, as usually in field theory, for example. It's a function of the Topf parameter. And how the instanton action depends on the Topf parameter is a very important aspect of this stuff, okay, of this story. Now, when when this starts with a non-zero value here, and this value is 4/3, and then it decreases, and at some point, which I'm going to call TC, it reaches 0, okay? So let's understand what is the meaning of these 2 points. What is 4/3? Well, 4/3 is the value of the, so 4/3 is the value of the potential at -1 minus the potential at 1. So you see here, the instanton action is just measuring the difference between the values of the potential of the saddle points in the theory of t equals 0. So this is actually the same kind of difference, the exponential kind of suppression that we would have found if we did the analysis for this integral. If we did the analysis for this one-dimensional integral, and we look at the two different saddle points, we would get exactly this. But of course, this gets t corrections. I like to emphasize this view of the matrix model as a deformation of a standard one-dimensional saddle points. And at some point you get Tc equal to 0, Tc A is equal to 0, and what is interesting is what is the meaning of this. So remember that Rajesh told us that there is a point in which all these functions that they compute have a 0, okay, or a pole or a branch cut, okay, have a singularity. Actually, this is exactly the same value. So this point in which amplitudes become singular is a 0 of the instanton action, okay? And this is very interesting because when the instanton action becomes 0, a sector which was supposed to be suppressed is no longer suppressed, right? And this is actually an important thing that can happen in large N theories. But let me actually emphasize another aspect of this, which is what is the what happens at this point. Well, this is precisely the point at which you do the famous double scaling limit, okay? So let me actually explain you how this goes. So it turns out that you can actually study this function near this point. So let me actually introduce a scaling parameter near this point, Tc minus t, and then you can see that A of t near this point goes like 8/5 3 to the phi 8 tau to the phi 4. Does it ring a bell? Does it ring a bell? Right? 8.5, tau to the 5.4, right? This looks very much like the instanton that we found in the Pan-Leeuwen story, right? Exactly. So actually, this is already zooming in the double scaling limit, and actually you have to introduce this parameter. The cosmological constant of 2D gravity is actually given by a constant, a normalization constant, Tc to the 4th divided by Gs. And when you do this with the right choice of C, which, I did this calculation carefully because I wanted to, I think it's 3 to the minus 1/8 or something like that. Let me just check it. I have never done this calculation, but I did it for these lectures. Yeah, it's 3 to the plus 1/8. So this is the normalization constant. When you do this, you can see that near this point, AT divided by GS goes exactly to the 8 square root of 3s divided by 5 times kappa to the 5/4. So in the double scaling limit, this instanton, which was due to eigenvalue tunneling, becomes the instanton of Pan-Leeuwen. Okay, so that's how you actually zoom in this at this point. This is precisely the point at which the cubic matrix model describes 2D gravity, and this is the double scale limit that Rajesh mentioned many times. But what I wanted to emphasize is how also the non-perturbative part of the cubic matrix model, including this effective potential, zooms into the Pan-Leeuwen instanton that we obtain from the double from the analysis of the Pan-Leeuwen equation. Okay. Now, so remember that here we also have this. So let me write here maybe. So here we have this. This spectral curve, and now what you can do is to try to do the double scaling limit directly at the level of the spectral curve. And this is also something which is very useful. So, the spectral curve, I didn't write it explicitly, but it also depends, this spectral curve, it depends on the effective potential, which depends on t. So this is going to be a complicated function of t, but you can also try to scale it near this point. And when you do that, you actually find that, it's, the actual spectral curve, let me write it here maybe. The actual spectral curve is x minus x0. Okay, maybe I'm going to keep the variable. I use lambda and x interchangeably, so don't worry about that. So this is x minus a, x minus b. So this is a relatively complicated formula. But what you can now try to do, here everything x0, a and b depends on t. These are non-trivial functions of t. You can try to zoom in this point, okay? And if you do that, you have to actually, you are going to actually zoom into this region here, okay? So you are going to send actually this cut to infinity, and you will concentrate on the region, because actually these 2 points collapse when Tc goes to 0. A and x0 get to the same point. So you have to zoom around this region. And, I explain you in the lecture notes how to do this carefully. And then, what you find is a very beautiful formula in which you have this double scale. So psi here is a scaling variable for x. So it's a local variable near these 2 points that collide. Scaling variable. And you see that when you do this, essentially, as I said, you are concentrating in this region here. So this point A is colliding with this point x0, okay? So they are colliding. That's why also this action goes to 0. But then you zoom over these 2 points, and then you get this double scale story, this double scale spectral curve. Let me actually again use color choke. And you see, since you are zooming here, this point is going to, you see, here now you only have a branch cut at psi equal to 1. So here you have 1. This point is 1. The branch cut, extends to infinity. But now you still have this critical point here, which is psi equal to. So this was in the x line, and this is in the psi line, which is, I say, is like a zooming of this region. And then you get here psi over minus 1/2. And of course, again, the action here, this 8 square root 3 over 5, you can think about it as an integral from 1 to minus 1/2 of I psi d psi, okay, divided by gs, okay. Okay. So the double scaling limit does this for you. And actually, Rajesh mentioned topological recursion today. You can actually reconstruct all the perturbative 2D gravity by doing topological recursion on this curve. Okay? By doing this, you would recover Painlevé 1, essentially. Okay? In another way. Okay? So we used this Painlevé 1 equation to describe 2D gravity, but you can also use this double scale curve to describe 2D gravity. And of course, the original curve would give you doing topological recursion of this curve, you would find the 1/n matrix model. Okay. Now, another thing which is very important is that now we have actually answered our question. We have now two families of periods. So the actually general answer for the Resurgent structure is that the possible Borel singularities of the 1/n expansion in this theory are going to be points in the period lattice generated by 2πit and by this action here. Okay? So here you will have some of these periods, then you will have this action A, and then there will be a two-dimensional lattice. Okay? And I think it's still an open problem to know for different values of the moduli of T what of these singularities are the actual Borel singularities. But what is important is that Borel singularities are always a subset of this period lattice generated by these two periods on the spectral curve. And in particular, you can ask now what is going to be the leading singularity. Well, if you actually are very near this t equals 0 point, this 2πit is going to be the leading singularity. But if you remove this Gaussian part, actually this is the action that controls the 1/n expansion. So for the 1/n expansion of this model, this is the action that is going to dominate. And then you have actually the statement that the FGTs of the one-cut matrix model go like A to the minus 2G times 2G factorial. Okay, where A is exactly the action that for an eigenvalue tunneling from AB to X0. Okay.
So why did you say it would be a subset? I mean, typically, can't you have multi-instant terms?
No, you could have, but you don't know exactly what are the combinations of these periods, which are, you have to do a much more detailed analysis. This analysis, as far as I know, has not been really done. Exactly for each value of T, what are the points on this period of lattice which are actual Borel singularities? I know, for example, that the first period and these 2πit and this A are going to be Borel singularities in some regimes. But in general, what is the linear combination of these which is going to be an actual Borel singularity? This is not yet known. Just to give you an analogy which might be misleading, or might confuse more, but think about the BPS spectrum of Cyber-Witten theory. This is also, we know that the BPS spectrum, the BPS particles are essentially linear combinations of monopoles and electric charges. Not all, so we have a lattice of periods also. These are, the BPS masses are going to be linear combinations of periods. You don't know what of all these points in the period lattice are going to be actual points on the spectrum, right? This is actually a very similar problem. We have a beautiful two-dimensional lattice with many points, but determining which one of them are actual Borel singularities of the theory is a difficult problem. You have to find essentially, actually we now know that the techniques that apply in cyber-Witten theory and the techniques that apply here are not very dissimilar, okay?
But I thought just physically you would think that you could take one eigenvalue, two eigenvalues, and so on. So,
absolutely. In principle, you could, you will have, the multiples of these p are going to be. But for example, what are the actual linear combinations of 2 pi it and at that are going to participate? Maybe that's trivial.
More,
maybe it's just one line and another line. But I think in principle, you have a matrix model knowing exactly what are the combinations of periods that appear as Borel singularities is not completely obvious. Okay, and
so for the
you
cubic matrix model, it has not been done. You're saying?
I don't think for say the cubic matrix model. Maybe for one cut is simpler, but for two cuts, for example, is much more complicated. Okay? You see, these are problems with the spectral curves, which are already relatively complex. It's similar to cyber-Witten curve. From the point of view of the mathematical structure of the theory, this theory is not much more simpler than cyber-Witten theory, for example, right? Yes?
I have a silly question. So maybe I should have asked it before the double scaling limit. So this cubic potential is ultimately unstable.
Yes.
And you can so you can tunnel very far away, not just to this local maximum. How can I see it from here, or can I see it?
No, but you shouldn't use quantum mechanical analogy here because this is a zero-dimensional problem.
Right.
Here essentially, you don't have time to tunnel to infinity, right? If you go to this critical point or this critical point, okay? So it's more like a question of what are the critical points.
But still, the potential goes to minus infinity.
But this is another issue. This is the question of how you would define this matrix integral from the very beginning non-perturbatively. But here we are working at the level of formal power series, right? So all these formal power series are well defined independently of the fact that the potential is bounded or not. The problem of how the perturbative sector and the non-perturbative sectors combine appropriately to describe a matrix integral with a convergent contour, that's a kind of more complicated problem, okay?
But I guess I'm asking, is there any way to see from the perturbative plus this non-perturbative expansion any ailment that will cause this model to be, like any avatar of this unbounded potential from below?
No, I would say that, at the level of formal power series, at the level of formal power series, of course, you see the structure of Borel singularities tell you that you can tunnel from one point to the other, and this is in a sense already, indicating some instability, right? But no, in principle, you don't see it here. Yeah, I don't think in the matrix model you actually see the potential instability directly in the power series. In quantum mechanics, it's easier to do it, but here, I think the formal power series are perfectly well defined, and you don't see necessarily an indication of that, I would say.
Yeah, but one related thing about this question, like, wouldn't you get a negative double derivative of V effective, which will give you an iota when you calculate and that probably indicates the instability?
Sorry, what?
Like, since this non-trivial saddle that you have is a maxima, the double derivative will be negative there, and when you calculate one loop...
But that just means that, that when you calculate, this is an exponential, this means that there will be an I multiplying here. Yeah, that's fine, but, that's, when we work with formal power series, we are not necessarily so worried about what is the exact value of the...
But had it been a minima,
No, I mean, what you could say is that the Stokes constant associated to this thing will be naturally imaginary, okay?
Okay.
And this you can actually calculate. You can actually calculate the Stokes constants here, and in particular derive the Stokes constant upon level 1 by doing this matrix integral in detail around this additional saddle. Okay, so this is something that I should say.
Okay, and another thing is, like, can I possibly have a background where I have a cut at the maxima,
Sure. You could have the two-cut matrix model in which you could put eigenvalues here. Yeah, absolutely.
Okay.
Yeah. Again, this is a formal sector of the theory. Here, in this story, if you want to not get confused, it's very important to distinguish the formal level from the non-formal level. At the formal level, it's very important to be able to construct whatever trans-series you want, whatever sector you want, even if they are around an unstable critical point. From the point of view of formal power series, this doesn't mean anything. This doesn't make any problem. So I think it's very important to first understand the formal level, and then if you want to go to the level in which, if this is integral converging, etc., this is another story. So it's important not to mix them. So in particular here you would say, yeah, how are you going to put eigenvalues in this unstable thing? Well, formally you can construct a formal trans-series, a formal series of two-cut series that people have, for example, used a lot even in relationship to supersymmetric gauge theories and so on. So there is no problem at all with doing this, okay?
Just quickly, so in the Gaussian you showed that the poles and this
yes.
imaginary IT, these were just simple poles.
Yes.
But now they become branch cuts? Or?
Yeah, absolutely. Yeah, thank you for your question. Actually, these are going to become branch cuts, and actually here you will have actually the same gamma 2G actually minus 5 halves that you would get in 2D gravity. So this is a branch cut, absolutely.
That's for the A, but even for the singularities on the vertical axis?
No, this one is still a double pole.
This will still be a pole.
This is really, this singularity is used to the conifold part of the free energy.
So
this is double
that doesn't change in any way. These will be like you showed yesterday.
Right. So before finishing, let me actually make a kind of an application of this formalism to just very quickly, I'm going to do it, to JT gravity, because this is something that people have done recently, and it is really like you can do non-protective FSD JT gravity now in 2 lines, okay? So let me give this as an example. So in JT gravity, actually, the starting point is a spectral curve, right? So this is how people define JT gravity, right? They define it with a spectral curve. So usually this is how you define it, okay? So let me actually write this in the same way that I wrote it before. Let me write this as mx square root of x, and mx will be the analog of my function here. Okay. Now, of course, this function has zeros, has many zeros, right? So all the zeros of these functions are actually 2 pi I square root of x are equal to pi k, right? So you actually see that, let me actually label like this, xk are k squared over 4 when k is an integer, These are the zeros of this function. And, we now can even calculate so you will have, you think about this theory here, what you will have is you will have a branch cut here, given by the square root, okay? Actually, maybe, let me write it, let me draw it a slightly different way. So this actually, so you will have a square root here for the square root, and then here you will have the first non-trivial critical point is going to be a 1,4 when k is equal to 1. This is k minus 0. And then you see that here, non-perturbative effects in JT gravity are going to be given by eigenvalue tunneling from this branch cut to this critical point. Okay, it's the same picture that we have in the cubic matrix model, right? So the action of these instantons is very easy to calculate. Is the integral from 0 to xl of yx dx, right? The same formalism that I have been using so far. And this is minus 1 to the L minus 1, L divided by 4 pi squared. And in particular, for L equal 1, so for L equal 1, you have 1 over 4 pi squared. And now we can get the large order behavior of the free energies in JT gravity, which is actually, these are the volumes on the moduli space the Weil-Peterson volumes, these are going to be given by my formula, by my universal formula. Phi pi square, maybe, yeah, it's exactly there. Here now, A is 4 pi square minus 2g, actually 2g because this is times 2g factorial. That's it. So you see, it's a one-line exercise with this formula is to do non-perturbative JT gravity, okay? And then, you get a very good estimate on the growth of the Weil-Peterson volume. So this is why I wanted to do this exercise. So this formalism, so this is in a sense all stuff, because, this is like cubic matrix model, double scaling limit, and so on. I have to say that away from the double scale limit, the calculation of non-perturbative amplitudes is more recent, and you can find in my papers with Ricardo Schiappa and Marlene Weiss very precise formula for the full correction to this formula with all the GS expansion. But you see the same formulas can be applied to these more modern theories of 2D gravity, because at the end, the formula is invariant, is using spectral curves. The perturbative sector is obtained by topological recursion on this spectral curve, and the non-perturbative effects can be obtained in the same way. Okay, let me finish here.
Do we have further questions? Okay, if not, let's go to lunch, and let's thank Marcos again. I remind you that at